So this is going to be another video about integration by parts with a worked out example. Again, we're acting like we don't know that we're supposed to do integration by parts, even though I just said that. So the main thing you're going to want to see is, first of all, is there a antiderivative rule for this? So let's just looking at this, I can see that there is no real antiderivative for that. There's a derivative formula for that, but there's not an actual antiderivative, so we're going to skip that. There's nothing that can simplify. There's no u substitution you can use, so the next thing on the docket is to try integration by parts. So that's what we're going to do. First thing we need to do is find what our u is going to be. If you remember the Lie8 rule of thumb, if there's a log, that should be your u. There isn't. If there's an inverse trig, that should be the u, which in this case it is. There's an inverse trig right here with this arctangent. Now if we do the derivative of this inverse tangent, you should get 1 over 1 plus x squared dx. Again, I multiply the dx over. If you don't understand what I just did there, you're going to want to watch the last video. I kind of explain why I do that. Now, the next thing we need to find is what our dv is going to be. Because if you remember the formula for integration by parts, you need the u, du, v, and dv in order to solve for integration by parts. So in this case, our v, the only thing that's left, so we already have this substituted for, we need the dx. So the dx ends up being your dv here, which means your v is just going to be x, because the antiderivative of 1 is just as x. Again, you don't need to worry about the plus c for now. All right, now let's set up the formula. I'm going to say this is equal to a, just to be lazy. I don't want to write all that out. So a is going to be equal to, well, we need uv first. So it's going to be x times the inverse tangent minus v du. V is x. So v is x. Du is 1 over 1 plus x squared dx. And then you'll see here that we actually have to use integration by substitution on this part right here. You can see that because the x squared's derivative is going to be 2x, and there's an x that shows up right here. So what I'm going to do is pull this out over here and solve this integral, and then I'll just throw it back in when I'm done. All right, so how this is going to look. First thing you need is your u. U is usually the most, this is a different u than the integration by parts u, but the u is usually the most buried function. In this case, it's going to be that 1 plus x squared. And why it's good to pick that one, because the derivative of that is going to be 2x. And we're trying to solve for x dx, because x dx shows up right here. So we're going to divide this by 2, multiply by dx. Divide this side by 2. So cancel, 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 cancel. Our x dx ends up being equal to du over 2. So now if I rewrote this green circle expression right here, it would look something like this. So if you substitute everything in, you would get x dx equal to du over 2. So I'm going to put a du over 2 here, and then it's just 1 over u, because the u is at 1 plus x squared, and the x dx, this part right here, is just going to be the du over 2. Simplifying this, you're going to end up with 1/2 times ln of u, which is 1 plus x squared. So I'm just going to put the 1 plus x squared in there, plus c. So now I'm going to put this part back into this up here to finish out this equation. So after I put this back into for the integral, we can solve for this a value here, which is going to be x inverse tan of x minus 1/2 ln of 1 plus x squared plus c. So you're going to want to take the derivative of this just to make sure that you did do the antiderivative correctly, which I believe you will. But it's still a good exercise to do it. I will leave that for you, though. I don't need to put that in this video. If you have any questions about any of this video, let me know.